Oh, good morning, everybody. Welcome to another exciting morning of chemistry, Chem 1211, with your host, me, Dr. White. Now, a couple of things. First of all, today I'm going to go over some information on test number 3, which I will give Thursday. I will do it like I did test 1 and 2 on Wednesday sometime. I'll post in Blackboard a PDF file that's password protected. Then on Thursday after our class, I'll email you the password and you'll have until 10 o'clock the next morning to take the test and send me your answers as a single PDF file. All right, we'll do that. Then after that, I'll do my world famous review for next test, in this case, test number 3. And after that, I'll go through the solutions problem set. I was thinking on my way home today from this morning, I was out and I got my physical therapy for my back, which is doing a lot better, but it's still not 100%, but still a lot better. And I'll do some more solution problems. We got time. We're on schedule. And then if we still have time, I'll start on chapter 15, which is for test number 4 material. And with that, I better get to work. We got a busy day ahead of us. Everybody see Blackboard announcements? Thank you. All right, I sent this out on Saturday. You also got an email. It's about test number 3. This Wednesday, you'll have till Friday. Remember, this is not an open note test, but I will have the last 2 pages, important information. You should go to the Blackboard lecture folder and you'll see important information, test number 3. Take a look at that because those are things you don't have to memorize. Just a reminder, you shouldn't be looking at any videos, talking with anybody else, or looking at your notes to answer the problems on the test. That's called cheating. I will do what's in my syllabus. In other words, contact the dean of students and my dean to let them aware that I think a student is cheating. I've done that in the past, unfortunately, when we've been in the classroom. I caught people cheating. Important thing, test number 3 will cover gases and solutions, which essentially chapter 11, 12, and part 1 of 13. Part 2 of 13 is essentially identical to part 1 in my lecture notes. Points breakdown, there are 48 points on gases, 57 on solution. It adds up to 105, and therefore there's 5 bonus points. Which 5 you pick, because I don't. This adds up to 105. Now, underneath your name, it will say, please use proper significant figures for all calculated answers. Use 3 significant figures for all atomic masses. If you don't, I take off a point. We'll have our normal Zoom lecture on Thursday, plus the lab. Last week we didn't have a lab. This week we will. I see someone with a question, or they didn't shut off their mic. And that's test number 3. Any questions? Going once, twice? All right. One thing I will ask you later, I'm going to try experiment. It didn't work yesterday in my class, but are you people hearing that clicking noise now still, or is it not there? If you're hearing it, give me a thumbs up. All right. I'm going to try something. Try shutting off that light. And that fan. Is it better now or still there? If it's still there, thumbs up. Now, I'm going to have to track it down. I was talking to a friend of mine over the weekend, and it might be a wall wart I have for one of the things powered from, the little things you plug into the wall. That can cause problems. I apologize, but anyways, let's continue on. Let me just log off here.
Dr. White, is everything is good? No sound, no clicking sound anymore.
Oh,
No,
good. All right, let me know when you hear it again. Thank you. It's the hardest problems to solve are intermittent problems because they're not always there. All right, good. Maybe it's the light. All right. Different thumbs up. Can everybody see test number 3 review on your screen? Okay, let's get going. All right, for test number 3, you should know, but I'll give it to you. When we talk about pressure, we use units of 1 millimeter or millimeter mercury in torr. 1 millimeter equal mercury equal 1 torr. We also have atmospheres abbreviated by ATM. And 760 torr equals 760 millimeters of mercury equal 1 atmosphere. And these are exact numbers. And we did this in the gas problem set. For gases, we use for the gas laws, temperature in Kelvin. I'll give you this, Kelvin equals degrees C plus 273. 273 is the exact number. Now, the first gas law, which we did problems, is Boyle's law. P1 times V1 equals P2 times V2. P1 is the initial pressure. V1 is the initial volume. Hang in there while I shut off proofing so you don't see all those little lines. And they're gone. P1 initial pressure, V1 initial volume, P2 final pressure, V2 final volume. Remember, you'll be given 3 of these variables. Usually you're always given P1, V1, and either P2 or V2, and you have to solve for the other. How do you do that? Whatever you're trying to get rid of, you divide on this side, and you have to divide on that side. Now, the ideal gas law, my favorite mathematical expression in chemistry, and that's PV equal nRT. P is in pressure in atmospheres, V volume in liters, N is the number of moles, K is temperature in Kelvin, R is the universal gas law constant, 0.0821 atmospheres, liters, moles, K. You'll be given all this. Now, first of all, remember that coming up now in the deep of winter, PV equal nRT tells you you should check your car tires because when the temperature goes down, the pressure goes down because volume, the moles, and R, which is a constant, all stay constant. And this is winter. And next summer, PV equal nRT tells you to check your tires again because temperature goes up in the summer. These N, R, and V in your tires are constant. Therefore, the pressure goes up. And like I said, 1995, that is, when I was driving around the highway, like 294, going to a place I worked in Gurnee, and coming back, when it was super hot, I think we had 2 weeks, the daytime temperature was over 100 every day. And you saw a lot of trucks and cars pulled over with blowouts because they didn't check their tire pressure and it went high when the temperature went high and pop, just like a balloon. Now, in using PV equal nRT, common mistakes students don't. Pressure has to be in atmospheres. However, you'll either be given this in torr or millimeters of mercury, you got to convert. I'll always give you volume in liters, so you don't have to worry about that. You'll never be given N moles. You'll have grams, which you have to convert to moles, and we've done that enough times. Temperature will be in degrees C. which you have to convert to Kelvin, which I just showed you. This is a constant, you'll be given that. By the way, R is a calculated number, and that's 3 significant figures. And that's PV equal nRT. And I'd recommend you go back and look at the problems I did either on the video or in the problem sets. Finally, in terms of laws, Dalton's law of partial pressures, the total pressure equal the sum of the partial pressures of each gas, and the partial pressure is the pressure of the gas it would exert if it were alone and not in the mixture. And we went through problems there. Now, I don't know if I did it in solutions or in gases, I forgot which. I think I did it in solution. Boiling point is when, of a liquid, is when the vapor pressure of the liquid equals the atmospheric pressure. Well, the higher you go on the Earth, the altitude, the lower the atmospheric pressure. Therefore, you need lower vapor pressure when you're boiling it, and therefore, the boiling point of a liquid is lower. So if you go on the top of the Himalayas, which is a place Dr. White will probably never, ever, ever go, because guess what? I am not a mountain climber. No, not my thing. Nothing wrong with it, just not my thing. But if you were to go up the top of the Himalayas and boil water, you'd find the temperature is a lot lower than here in Chicagoland, because the pressure is lower. Let's find out something. And if you go to the top of Mount Everest, which is not the top of the Himalayas, but you're still pretty high. Is that in the Himalayas? I don't know. My geography is now lacking. The boiling point of water, instead of 100 degrees, is 68 degrees, and that is way lower. So that's something you should know. All right, let's check and see if Zoom is live. Everybody see solutions on your screen now? Okay, thank you. All right, now let's move on to solutions. And when we talk about solutions, that's the mixture of 2 or more compounds or substances mixed together, and neither loses their chemical identity. When we talk about a solution, things you should know, hint, hint, wink, wink, say no more. And that's a solvent is the component of the solution that's present in the greatest amount, and the solute are the other components. And you can have only one solvent, but many solutes. So if I were to have 25 grams water, 10 grams sugar, and 5 grams, oh, let's say sodium chloride beats past the nickel. Which are the solvent or solvents and which are the solutes of that solution? I'm going to share and let you have some fun. So, go. And when you're done, smile, or if you're not on video, give me a thumbs up. And Dr. White has an announcement to make, and that is because of my back and other things, I got behind in things. I've graded up-to-date grading your labs per Sunday Later today or tomorrow morning, I'll upload those grades to Blackboard so you can see them. I apologize for getting behind. The other thing which I haven't done, I realize now, is send out an email to all of you, and you should have gotten an email from the school. I think it's from STEM Division or something like that, talking about a rebate you can get for your chem kit. That's real. It's not a phishing email. Go ahead and submit it and get your rebate. Or as my father used to say, if you're not prepared to put that money down on the sidewalk and walk away from it, it's something you want to keep. It's good money. Sound advice. He always did give me sound advice. All right, let's take a look at this. What's the solvent of the solution? And the answer is water. Why? Because it's in the greatest amount, 25 degrees. What's sugar and salt? Those are solutes. All right, now, at first glance, there's something you'd think is a solution, but it's not. We call that a colloidal dispersion. And those are particles not really dissolved, but suspended in a liquid, another liquid. And how can you tell you have a colloidal dispersion? And unlike a solution, a colloidal dispersion scatters light. Time for Dr. White to play with one of his many flashlights. Here's my tea. Oh, look, you can see the light coming through. Guess what? It's a solution. Actually, a complex solution, water, sugar, and the different chemicals that are in tea leaves. Now, if you were to do the same thing with a glass of milk, which I don't have one handy, it'd look like this. You can't see the light coming through because the particles in the colloidal dispersion scatter the light. How's that for a great demonstration? And you should know colloidal dispersion is not a true solution, or not even a solution. And I don't have here, but what are some examples you should know? Everybody see colloidal dispersion on your screen? Hold on. You should see it now. Can you see it? Give me a thumbs up. Thank you. All right, what are examples of colloidal dispersion? Well, milk, you should know. Another one is latex paint. Do not try a flashlight thing at home, but your blood is a colloidal dispersion, and so is mayonnaise. I'll just call it mayo. And if you look at it, ketchup is too. So you should know examples, at least one, what is a colloidal dispersion? And you should know what it is and the fact that a colloidal dispersion scatters light. Now, next thing I taught you was the rule of thumb that you should know. This is very important. See, I even wrote it on the paper. And that's light dissolves light. And what it means is like solutes are soluble in like solvents. And what we really mean are polar solutes are soluble in polar solvents, and nonpolar solutes are soluble in nonpolar solvents. An example you should know, and I won't give this to water, alcohol, and salts like sodium chloride, and also one more I'll put up here, sugar, which is really an alcohol, but you don't know that, are polar. And nonpolar things, Vaseline, vegetable oil, gasoline, baby oil, grease, and dirt, are nonpolar. Oh, look, I was being subtle. And know this. And we talked about, we did a polarity problem. Is something soluble in water but not in gasoline? Is it polar or nonpolar? And the answer is it would be polar. Why? Light dissolves light, and water is polar. It's soluble in that. Gasoline is nonpolar. The unknown compound is not soluble in that. Now, when we talk about solutions, there are certain definitions you should know. This, I won't give you an important information. I'm going to make you memorize little things, learn some stuff on your own. Solubility of a solute, that's the maximum amount that will dissolve in a given solvent. If I'm at the solubility limit of salt and water, I can't put one more molecule. It'll just fall to the bottom, which we call precipitate. Now, saturated solutions contain the maximum amount that can be dissolved under that conditions. A dilute solution contains only a tiny amount of solute that you could dissolve in that solvent. Now, concentrated, you have a lot, but not at the saturated solution level. Finally, you should know aqueous solution is a solution in which water is the solvent, and that's indicated by bracket AQ, close bracket. Now, there are different ways of measuring how much solute is in a solution of a certain solvent. And there's percent concentration by weight, by volume, which I shut the switch, will this be on test, to the off position, but I turned it all the way up and passed all the way up for molarity. And molarity of a solution, you should know, I think I give you this important information. Wow, look, I even wrote this and this here. Molarity, and it's indicated by a capital M. Moles of solute per 1 liter, but in a lab we use 1,000 milliliters. So you should know how to use this. And let's take a break to have you try something.
Dr. White is clicking.
I didn't switch. Whoever told me, wait, can you see the words "what does"?
Yeah, but the clicking sound is bad.
All right. All right, why don't you try this one? What is 2.475 capital M KOH mean? I'll let you try it, then I'll do it. You get 10.2 seconds, go. I'll give you a bonus 5 seconds. 4.9, 4.95, 4.955. Time's up. What does this mean? As soon as you see capital M with a number and a structure formula, that means molarity. And what does this mean? 2.475 moles KOH per 1,000 milliliters, or you could have put a liter. Let's do another one. And let me have you work on this one. What does this mean? 4.16 times 10 to the squared, capital M, NaCl, bracket AQ, close bracket. And what is the solvent of the solution? Go. And when you're done, give me a thumbs up. Anybody need more time? Going once, twice. All right, I'll give you an extra 4.2 seconds. 1, 2, 3, 4, 4.05, 4.1, 4.15, 4.16. Time's up. What does this mean? As soon as you see a number, capital M, and then a formula, you know that's molarity. Molarity, moles, 4.61 times 10 to the squared, moles NaCl per 1,000 milliliters. What's the solvent? You know what the solvent is by bracket AQ, close bracket. That tells you this is an aqueous solution, and the solvent is water. And that's how you do it. Now, there are two problems, and I'm going to go through that in a little while in the solutions problem set. And one of them is to determine how many moles in so much solution, and I'll go through that. Remember, I haven't done this all day yet. For test number 3, don't forget, use your good buddy, your good friend, unit analysis. I love that. But seriously, use your good buddy, your good friend, unit analysis, both for gases part and solutions. And we talk about one of the types of problems, which I will give you, it's a two-step molarity. Step 1, you go from milliliters to moles, and step 2, you go from moles to grams. Now, just a reminder, remember 1 mole of a compound equals atomic weight of the element in grams, or 1 mole of an element. 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of a compound is the sum of all atomic weights. And that's the review. Any questions? Remember, on a serious note, there's no such thing as a dumb question in my class or anywhere in my life. Always feel free to. Time for a public service announcement from Dr. White. Don't forget, tomorrow night, I will have my office hours from 6 until 7:15. If you have any last minute questions, come on down, say hello, stop by. I'll be here in my classroom, COD North, really my office in my home, as you can see all the good stuff behind me. And don't forget, do the practice problems. That will help you get a good score on test 3. All right,
Dr. White, what is that, the last problem we did? What is that in the parentheses? What is the abbreviation in the parentheses? We did the last problem. Could you?
Mean where the two-step?
No. We just did the last problem. Something was in the parentheses. Could you?
Oh, okay. First of all, thank you for your question. All questions are good questions. Can you see that now?
Yes.
All right, let's blow this up with my super fantastic magnifying glass. You see that now? It's
Yes.
A and a Q.
Okay.
AQ tells you aqueous, the solvent is water.
Okay.
Let me say it again so you can write it down. It's important. Bracket AQ. That looks more like a G. Let me, hold on. Instant replay. There, that looks better. My first grade writing teacher would be happy now. AQ, aqueous. When you see that in a bracket, that tells you the solvent is water.
Thank you.
Aqueous solution. Now, non-aqueous, the solvent is not water, but I've never put that on test. Oh, did I just give that away? Bad, Dr. White. All right. Any last other questions? I don't know why I do that because I got these speakers turned up. Notice I don't have my hearing aids in, which is nice. All right, let's move on. And let's look at the problem set for chapters 12 and 13. Everybody see that on the screen now? Thumbs up, people. Thank you. All right. First of all, I'll give an example of colloidal dispersion that you can use in your daily life. And you could use latex paint, milk, blood. You could also use ketchup, mayonnaise. Those are all good ones. Give an example of a solution that you could use in your daily life. And we could have tea, pop, by the way. Dr. White is from Chicagoland, except for the 5 years I lived in Michigan when I got my PhD at Michigan State. And the stuff you get in a can or a bottle, plastic bottle, that's carbonated and non-alcoholic, we call that pop, not soda. I have to think of what they call it on the East Coast. I don't know what they call it on the West Coast, whatever. But anyways, pop, like 7-Up, Coke, or good stuff, Dr. Pepper, Verner's. Now, a solution has 12 grams of KBr, 10 grams of water. What's the solvent and what is the solute of the solution? The solvent is the component present in the greatest amount. In this case, not water, it's the potassium bromide KBr, because 12 is greater than 10. I hope you all know that. And water would be the solute. Now, we just did this one type. What does this mean? As soon as you see capital M, what does it mean? It means molarity. And molarity is 1 point, in this case, 34 moles of HCl. You'll learn later on, next 2 chapters from now, that's hydrochloric acid per 1,000 milliliters. And notice here I have what does 4.56 times 10 to the third capital M NaCl, a bracket AQ close bracket mean? And what is the solvent? It's 4.56 times 10 to the third moles of sodium chloride per 1,000 milliliters. That's what this means. What's the solvent? AQ in a bracket. Like that tells you water is the solvent. See, I wasn't lying earlier. It says it on the problem set too. Boy, that was a lame joke. All right, now let's look at some of the problems. Let's look at number 8. And the question is, how many moles sodium chloride are in 125 milliliters of a 3.45 capital M NaCl solution? So the first thing you should do, what are you being asked to find? How many moles sodium chloride? What are you given? 125 milliliters. What else are you given? Well, this number that's 3.545 with a letter, capital M, then a formula. And what does that mean? Capital M, molarity, moles solute per 1,000 milliliters. Therefore, this is 3.45 moles of sodium chloride per 1,000 milliliters. Now, the 125 is all we have to start with. And we're trying to get to moles of sodium chloride. And it's time to use your good buddy, good friend, unit analysis. For those of you getting sick of that, only a couple more weeks. All right. Whatever you're trying to get to goes on top of the ratio. Follow this red arrow. Whatever you're trying to get rid of goes underneath, milliliters. Where do you get the numbers here and here? From this, which you knew came from here. It's 3.45 moles of sodium chloride per 1,000 milliliters. Milliliters divided by milliliters cancels out because anything divided by itself equals 1. I'm left with moles. This is 3 significant figures, 3 significant figures. The 1,000 is an exact number and does not play a role. So when you're multiplying and dividing, the number that has the fewest significant figures that you're multiplying and dividing is what your answer should be. 3, 3. My answer has 3. All right, let's try a little different one from here. And I'm going to let you try one. No, we don't have enough time. Let me, oh, actually, we do have enough time. And why don't you try this one? How many moles of H2SO4 are in 461 milliliters of a 1.45 capital M H2SO4 solution? Your turn. If you don't have a calculator, just try setting it up. Remember, find what are you being asked to find, what are you given, and use your good buddy, your good friend, unit analysis. And when you're done, give me a thumbs up or a smile or both or none of the above. Again, if you're done, give me a thumbs up. All right, I think everybody's done. If not, scream. No, don't scream. All right, let's do this. All right, what are you being asked to find? How many moles of H2SO4? What are you given? Well, you're given a volume of the solution, 461 milliliters, and you're given this, 1.45 capital M H2SO4. In chemistry, as soon as you see capital M, that means molarity. So what this really means is 1.45 moles of H2SO4, that's sulfuric acid, per 1,000 milliliters. Now, we only have really one number to start with. That's 461 milliliters. And if I had a ratio that I can convert it, what do I want my answer to be? Moles of H2SO4. And since I've already done it a couple of times today, I won't do it again. So you just do it mentally in your mind. Hear the whistle. It's time to use your good buddy, your good friend, your analysis. Whatever you're trying to get to goes on top of the ratio. Whatever units I'm trying to get rid of go underneath. And now I can put that in there. I want on top moles H2SO4. I want underneath milliliters. Where do I get these numbers? Right here. 1.45 moles of H2SO4 per 1,000 milliliters. This is three significant figures. Uh-oh, I'm in my rut again. This is three significant figures. This is an exact number. So my answer should have three significant figures.
Dr. White, would there ever be an example where one, like the 461 might be four character, four significant
I'll
figures?
tell you what, let's do one after this one.
Okay.
Good question. All right, so now just remember milliliters divided by milliliters equal 1. I'm left with the right units. So now I can go to my calculator and let me open my calculator first. I see somebody beat me already, so let me do it. And we'd have 460, hold on, plus 461 times 1.45 divided by 1,000, hit, and I get 4.6845000. Now, this should be three significant figures. How do you round it off? Keep the 6, keep the 6, keep the 8. Use the 4 to round off. Is that 4 or less? And time's up, it is. So I drop that 4 to 5 and the zeros. So I will get 6.68. Wrong thing. Hold on. And the answer here would be, my memory served me correct, and that's how we do it. Now, if I look at the clock, oh, let's go, we'll go a couple minutes over and I'll still give you your break. By popular demand,
Dr. White, I think 6.68, right?
was it 6.68? Hold on. Yep. Uh-oh, I gotta eat more fish. My memory's going. You know, some things I draw it out. Let's take a break now. I'll give you an extra minute or two because it allows me to go stretching. Come back at 10:55. That's when the big hand is on the 11. For those of you with digital watches, 10:55. And I'll see you in about 5.5 minutes or so. And we'll go through that problem that I was about to write here. So I'll see you in about 5 minutes, 10:55. What? Who had a question? Nope. I'll be right back in a couple minutes. time to start again. It's time once again for that, your favorite show, internet show, Chemistry with Dr. White, starring Dr. White. That was pretty lame. All right, let's go back to, I had a special request. And you all should see how many moles NaF, that's sodium fluoride. And let me read this for you to try. How many moles of sodium fluoride are in 4.444 times 10 to the fourth milliliters of a 5.555 capital M NaF solution? By the way, sodium fluoride is what's put in your toothpaste and also in your water to fluoridate it to keep your teeth healthy. And when you're done, give me a thumbs up, but take your time. Don't let me rush you. Get done quick. Get done. No, I don't rush students. By the way, is that clicking noise gone or is it back? If it's gone, give me a thumbs up. Thank you. It might be that light. I'll just have to cover my forehead from the light reflection or get a new light. All right. Remember, give me a thumbs up when you're done. Be nice if they could do a thumbs down if you're not done. All right, I think everybody's done. Let's get moving. All right, now, question is, first of all, for this question, what are you being asked to find? And the answer is how many moles sodium fluoride? What are you given? Well, you're given this, how many milliliters of solution you have, and you're given this. And as soon as you see capital M, that's molarity, you know that really means 5.555 moles sodium fluoride per 1,000 milliliters. So the only thing I have to start with is my milliliters. If I could convert it, what units do I want my answer to be? Well, we took time to figure that out. Moles sodium fluoride. And now I'll use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top of the ratio. Whatever units I'm trying to get rid of go underneath. And therefore, if I write it in, I have moles sodium fluoride per milliliters. Where do I get that number or those numbers? From here, the molarity, which is 5.555 moles of sodium fluoride per 1,000 milliliters. Now, this is, ooh, he got out of his rut. Four significant figures. This is an exact number, doesn't play a role. Which is the lowest number? Things are multiplying and dividing. There are significant figures, and the answer is 4. So our answer should be 4 significant figures. And now it's time for Dr. White to go to his calculator. And here's the number I get. Now, first of all, thumbs up, people. Can everybody see it? Everybody see? All right. Now, I'll let you do it first, and Dr. White will do it. Round that off to how many significant figures? 4. Time's up. Put down your pens and pencils. Hand in your computer. And let's do this. Now, this has to be 4 significant figures. Keep the 2, keep the 4, keep the 6, keep the 8. Remember, this is 4 significant figures. Use the 6 to round off. Is that 4 or less or 5 or higher? 3 more rings. 2 more rings. I think 1 more. This is the last one, or 1 more. This is the last one. Bye. Somebody I don't know. They don't know me, which is why I don't answer it. Even if I did, I wouldn't, because I'm talking to you. All right, let's go back. We need 4 significant figures. Keep the 2, keep the 4, keep the 6, keep the 8. Use the 6 to round off. 5 or higher, drop these numbers. Increase this by 1. So that'd be 2.469 times 10 squared. And let's see if Dr. White can remember that. Hold your breath. Let's see if he can remember it. And that would be the answer. Remember, this is 4 significant figures, which is why I rounded it off. And that answers a question of one of your colleagues, how to do this with 4 significant. And if this were 4 and this were 5, it would still be, if this were 5, this were 6, we'd have to use 5 significant figures. Remember, when you're multiplying or dividing, the answer should have the same number of significant figures as the number you're multiplying, dividing, that has the fewest significant figures. And this problem, we had 4, 4, and when you have an exact number, that plays no role in calculating significant figures. All right. All right, let me just check. Choose. Thumbs up, people. Do you see the problem? How many grams NaOH? Thank you. All right, let me do this one, and then I'll let you do one too, because I share in the front. Fun. 10 points. How many grams of sodium hydroxide are needed to make 4.651 times 10 to the third milliliters of 1.23 capital M NaOH solution? So what are we trying to find? Grams of NaOH. What are we given? 4.651 times 10 to the third milliliters of solution, and you're given this number. And what this really means is when you see capital M, that's molarity, 1.23 moles sodium hydroxide per 1,000 milliliters. Now, there's no way I can go from milliliters to grams directly. And therefore, you need two steps. Step one, and this will be given to you in important information. You go from milliliters to moles. Step two, you go from moles to grams. And therefore, let's do step one. What do we have? We have 4.651 times 10 to the third milliliters of solution. We want to go to moles. In this case, it's moles of sodium hydroxide, because we're eventually going to go to grams. So how do we proceed? Use your good buddy, your good friend, unit analysis. Whatever you're trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. And I can write that in. And therefore, where do we get these numbers? From this. Because we knew this meant this. And there's 1.23 moles of sodium hydroxide per 1,000 milliliters. Now, I'm going to make you work hard today. Before you pick up your calculator, everybody think about, and then I'll tell you how many significant figures should your answer be. Not what it is how many significant figures. Time's up. How many significant figures? All non-zero numbers are significant. 1, 2, 3, 4. 4 significant figures. How many here? Ooh, 1, 2, 3. 3 significant figures. 1,000 is part of a definition, therefore, and it's an exact number, which doesn't play a role. This is a multiplication division. The number of significant figures in your answer is the same as the number you're multiplying and divided with the lowest. And I hope you all agree 3 is lower than 4, so our answer should have 3 significant figures. And now I'm going to write this down because I'm going to forget it if I don't. And just to be sure, notice milliliters divide out. I'm left with moles. So now I'm going to go to my calculator. and this is the number I have. Now, this is a two-step calculation, and there are two ways you can round off. Wait until the end or each step. I will calculate both for the test if I have something on a test. And notice we want three significant figures, and therefore this would be 5.72. Even though my calculator is set up for bigger, but I've rounded it off to three significant figures. Are we done? No, we have moles of sodium hydroxide. We're trying to get to grams of sodium hydroxide. So now I have to do step number 2, moles to grams, which you learned hopefully for test number 2. And here I have 5.72 moles of sodium hydroxide. And what do I want to get to? Grams of sodium hydroxide. And I'll use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes there. Ooh, where do I get to? First of all, let me write them in. And where do I get these numbers? Well, in important information in test 3, 1 mole of a compound equals the molecular weight in grams of the compound. And the molecular weight in grams of a compound, this will be given to you, is the sum of all atomic weights in grams. Well, sodium, oxygen, and hydrogen. Why? Because that's what's in the molecule. Sodium is 1 times, if you look at the periodic table, the 3 significant figures, 23.0. Oxygen, there's 1 of them, 16.0. Hydrogen is 1, and it's 1.01. Do the math, 23.0, 16.0, 1.01, add it up. Now, when you're adding, you get the same number of significant figures in your answer to the right of the decimal as the number that has the fewest significant figures you're adding. This is 1, 1, 2. So I'm going to round this off, keep 1, use that to round off. It's 4 or less. So the correct number is 1 mole of sodium hydroxide is 40.0 grams. Now, I'm going to fade prompts, that's a teaching thing. How many significant figures should your answer be? I'll tell you in a second, but you try right now for this step 2. Time's up. All non-zero numbers are significant, so 5.72 is 3 significant figures. 1 is part of definition. Its exact number does not play a role. Non-zero numbers are significant. Zeros at the end with a decimal point are. So this is 3 significant figures. Therefore, my answer should have 3 significant figures. Notice moles divided by moles equal 1. I'm left with the right units. So now I'm going to go back to my spreadsheet. And notice if we round this number or this one, oh, I'm gonna get fancy on you. What's in red to three significant figures? Oh, look, we get the same number. And the three significant figures, both would be 2.29 times 10 squared. That's both ways. You round off at each step or at the end. Well, it's time for Dr. White to let you try one. I won't give it to you. Let's read the problem. How many grams of sodium chloride, NaCl, are needed to make 4.567 times 10 to the third milliliters of a 1.234 molar NaOH solution? Now, you'll need for this problem, hint, the atomic weight of sodium and chlorine, which you'd find from the periodic table. You know how to do that. But since you might not have a periodic table, I'll give that to you. And since you might have forgotten, here are the two steps you need to know how to do. And it's your turn. Go. Oops. Sorry about that. I was just looking out in the real world, seeing what's happening. You don't want to look. If you don't have a calculator, just set it up. Remember, start out, what are you being asked to find? What are you given? Oh, for a person who asks, I'm going to check with the department about what to do with if you don't want your chemical kit, you're done with it. And I'll check. I have no idea if they'll allow you to donate it to another student, because I would think so, but just because I do doesn't mean there are other barriers that I'm not aware of, like liabilities that the school doesn't want to be involved in. But I'll check. Or you can always try selling it on eBay. And when you're done, give me a thumbs up, but take your time. I shouldn't ask, but is the clicking noise gone? If it's gone, give me a thumbs up. Oh, good. Maybe it's the lamp. And as always, sometime later today or later this afternoon or early evening, I'll have today's Zoom meeting posted on YouTube, where Dr. White's a YouTube star. For only $19.95 plus shipping and handling, you can have an 8x10 signed autographed glossy of Dr. White. Not. All right. Anybody need more time? All right, I think everybody's done. Everybody done? Let's do it. All right, what are you being asked to find? How many grams sodium chloride? What are you given? How many milliliters of solution you have to make? What are you also given? Ooh, this number with a capital M, 1.234 capital M NaCl. Oh, too much. And as soon as I see a number, capital M, in a chemical formula, I know capital M in chemistry is molarity. And that's 1.234 moles NaCl per 1,000 milliliters. Now, there's no way I can go from milliliters to grams. You can't. But I now know I need to use two steps. Step one, I go milliliters to moles. So I'm going to do that. And here we have 4.567 times 10 to the third power milliliters times some ratio. What do I want to get to? Moles of sodium chloride, because eventually we want to get the grams of sodium chloride. So now I'll use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. And I'll put those in. And I have milliliters here, moles, NaCl. And where do I get these numbers? From this right here. The molarity, which is really 1.234 moles of sodium chloride per 1,000 milliliters. Now, oh look, this is 4 significant figures. You should know how to figure that out. This is an exact number. This is, 4 significant figures. So my answer here should be 4 significant figures. Why? Because when you do multiplication and division, you look at the numbers of significant figures of your numbers. The number with the smallest should be your answer of the number of significant figures. And now I'll go to my calculator. That's the number iCalculator gives me. I'll let you try first, then I'll do it. Round that off to 4 significant figures. Time's up. Keep the 5, keep the 6, keep the 3, keep the 5. That's my 4 significant figures. The next number is what I use to round off. That's a 6. It's 5 or higher. Drop this and the rest. That becomes, the 5 is increased by 1. So the correct answer to the 4 significant figures, 5.636. And that's how many moles. Let's go back to our problem. But I'm trying to get 2 grams of sodium chloride. So now I have to do step number 2, which you learned hopefully for test number 2. Ooh, it rhymes. And that's going from moles to grams. And here we have 5.636 moles sodium chloride. I want to go to grams of sodium chloride. And I'll use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. And those numbers, where do I get these? Well, first put the units there. And remember, 1 mole, this will be given to you, of a compound equals the molecular weight in grams of the compound. And the molecular weight in grams equal the sum of the atomic weights in grams. And if we look here, I gave you those numbers, but you can find these from your periodic table, the atomic weight, and sodium chloride has 1 sodium, 1 chlorine, 23.0, 35.5, add them up, 58.5. Notice 1 past the decimal, 1 past the decimal, 1 past. So for every 1 mole, I have 58.5. Now, how many significant figures, I'm going to let you try first, and I'll tell you, should my final answer have here? Time's up. This 1 is an exact number. This has all non-zero numbers are significant, 1, 2, 3, 4. This number has 1, 2, 3, so it's 3 significant figures. Which is lower, 3 or 4, and time's up. Hopefully you picked 3. So my answer should have 3 significant figures. And now it's time for me to go to my calculator. Nope, not yet. Remember, moles sodium chloride divide out. This divided by this. Remember, anything divided by itself equals 1, which is gone. I'm left with grams of sodium chloride, which is what I want. Now I can go to my calculator. All right, now I'm going to let you either column A or B, I'll highlight it in red, round that number off to 3 significant figures. It's a little more tricky, but you try it first. I'll give you 8.7 seconds more. 7, 8, 8.2, 8.5, 8.61. Time's up. And if we look over here, we have 3 significant figures our answer should be. Keep the 3, keep the 2, keep the 9. Use the 6 to round off here. Same thing here, use 7. You drop these numbers, increase this by 1, 9 becomes 10, which increases this. So the answer would be 3.30 times 10 squared. And that's how many grams you'd have to weigh out to make that solution. And that's how you do it. And that should help you with, I see a question, hold on. It'd be times 10 squared. Notice this is 60 times 5 would be 300. Therefore, you do need just 10 squared. Let's go back and look. On my spreadsheet, notice E plus 0.2. That means E is 10 times 10 squared. And hopefully that helped whoever wrote that down. All right, any more questions on anything on solutions? I'm all ears. Actually, they are getting bigger. Did you know it's a sad fact of life? Your ears keep on growing. By the way, I can wiggle my ears. Am I cool or am I cool? Nah. All right, let's move on. Let's see. And the answer is, of course, I can show you it again.
The other, Dr. White, the other worksheet, the one that you were writing out the problem on.
Oh, okay. Spreadsheet. Hold on. Oops. Does that help?
Yes, it does. Thank you.
Now, the nice thing is, if you ever miss something like this, you can go to YouTube, my Chem 1211 YouTube channel, and find this part of the video, stop it, and look. Is that cool or is that cool? By the way, don't forget, if you put anything in ratemyprofessor.com, they still allow you to give the chili peppers for hot chem faculty. Obviously, they should have ice cubes for those of us who are really cool. That's awful. All right. Any other things? Let's, oh, I see another question. Oh, I already did that. All right. What I like to do now is move on to the next chapter. And this is chapter 15. We're going to skip over 14, do 15. This is better for you. Whoever wrote the book, if you bought the book, they put the order of chapters, how should I say this? Incorrectly. I'll be polite. All right, this is not on test number 3. This is test number 4 material. And let me make you see that, or let you see that. We got a few more minutes, so I'm gonna get started. All right, now, the problem somebody has asked me in non-scientific notation, would the answer be 330? Well, sorta, but this is one of those things where 330 is only two significant figures. By writing it in scientific, I could do 3. So therefore, I'd probably take off 100 million points on a test if you did it that way. Maybe not. Actually, I would do my tests, which I always do, so this would never occur. It would be like 331, so you could have 3.31 times 10 squared, or 331, and both of those would be 3 significant figures. But when I'm doing problems in class, I'm doing things on the fly, picking up, deciding what numbers. So sometimes this happens, which is real life. All right. Now, this chapter is exciting stuff. I'll teach you about something you don't know the word yet, chemical equilibrium. And these are things that are going on inside your body too. And we'll also talk about rates of reaction. How fast is a reaction going? Not all reactions go at the same speed. And if you have the book, which hopefully you didn't buy it, but if you did, I'll be presenting extra material that's not in your book, because Dr. White's a chemist and knows the stuff you should learn. All right, switch is on. Now, let's talk about collision theory and chemical reactions. Now, I'm never going to ask you specifically describe what this collision theory is, but I will ask you about what are key factors. Now, the collision theory is a statement of a set of statements that gives conditions that must be met before a chemical reaction must take place. In order to have two things react, this has to happen. Now, there are 3 conditions. And now the switch is on. And let me go through these, and then this Thursday, I'll pick up again. The first one is, in order to have a chemical reaction, reactants must collide. In other words, if I have 2 elements or compounds, for them to react, they have to collide. So if you have a beaker here and a beaker here, guess what? They won't react. You got to mix them together so they can collide. And that's the first step in order to have a chemical reaction, or first key element. The next thing is they have to have what's called enough activation energy. And colliding particles, this is also, know this, and I'll go about a minute or 2 more over, please bear with me. Colliding particles must possess a minimum amount of energy, called the activation energy, if the collision is to be effective. That means you get a chemical reaction. The amount of energy is, this is to break bonds. It's in that color, because you don't have to know that. Another way of saying that the activation energy is the minimum combined kinetic energy that particles react must possess. Remember the first one, which is why I have it. So that means if you have 2 compounds or particles coming together, they just go like this, nothing's going to happen. They got to go boom, boom. And so there's enough energy, so they react. Oh, look, my hands reacted. That was pretty awful. But got the message across. So you got to have enough energy. And finally, the last statement for the collision theory is, for certain molecules, they have to have the proper orientation, unless they're very small. So the key thing here to remember, which you should know, when you have molecules colliding, they must have the proper orientation. What does that mean? Ooh, very expensive demo time. My house key. And if I put it in the lock this way, upside down, the key won't go in. It's got to go in this way, and then I can open the lock. By the way, there are locks for my shed and my other stuff around the house. This is my house keys that I always carry. And therefore, when two molecules are coming together, they have to have the proper orientation. It's like this, oh no, they don't come together. They have to have the proper orientation. And that's very important, especially in your body. Certain of your enzymes and other proteins, they have to be oriented properly to react to make things that are going on in your body. With that, if I look at the clock, oh no, I went over by a minute or two. And so I'm going to say, bye, gehen gesund. Don't forget, Thursday we'll have our regular class Zoom meeting and lab. At the end of the lab or at the end of our meeting, I will mail out the password for test three, and you'll have until the next day, 10 a.m., to take it and send it up to me. With that, I'm going to say bye. Have a great day. Enjoy the rest of the day and tomorrow. Remember, do the practice problems. Go back and look at the videos. They're free of charge. Actually, you have to pay to be in my class, but on the YouTube, I think they're, oh, you can always make a donation to Save Dr. White Foundation, care of somewhere. With that, bye.